Good. So this is largely a sociological talk about, the changing models of how scientific computations are done. And so over the last 100 years, we have seen a movement from the era of manual production of scientific data in small experiments to the industrial revolution of big science. And so in the 1920s, we started out with small experiments done by individuals in small groups, which were slowly growing in scale. And after the 1960s, the national laboratories were built and the first big science projects really started in earnest. And one can see this very nicely through the evolution of nuclear physics into high energy physics. So we first had the Van de Graaff generators, then the cyclotrons were built in Cambridge, then synchrotrons, national laboratories. And then the options were either a single country builds the next generation of facilities, which was the SSC, which turned out to be too expensive even for the United States. And then the whole world teamed up to build the Large Hadron Collider. And the emergence of the big science is a big difference in many ways. So in the past, the small-scale experiments rapidly followed one another, and the data sets had a relatively short life, and there was no problem in publishing the data, putting the data in the appendix of the papers. But today, the big science experiments like LIGO, LHC, Square Kilometer Array, LSST, OI, NEON may not be surpassed by another version of the experiment in our lifetime. So as a result, the data is here to stay for decades. And so the science environment around the turn of the 20th to 21st century was largely bimodal. So there were the small-scale SPI projects on one end, and then the big NSD, MREFC projects, the big science projects on the other end. And it's really changed over the last 20 years quite a lot. There's much more happening in the middle. And the NSF started to support the mid-scale projects, the various mid-scale infrastructure projects. NIH introduced the UO1s. There were private collaborations, public-private partnerships like the Human Genome or the Sloan Digital Sky Survey. And typically, this is very exciting, and it's changing the way we do science. So the typical pattern in this mid-scale project is to create a unique instrument, a new kind of electron microscope or a cryo-EM or a small-scale telescope, use cutting-edge technology, take lots of risks, push the budgets to the limit and sometimes beyond to maximize the science and generate large amounts of data because everything is computerized and automated. And in this process, there was an enormous amount of fresh creative energy liberated. So the PIs are typically associate professors, full of energy, pushing, and because the scale of the project is smaller, they can stay much closer to the technological edge. And so today, this is really turning into the sweet spot for science. So the most agile population of scientists. And there is another interesting characteristics that they typically don't want to build their own computer centers. They want to maximize the science. They don't want to spend much of their money on computer hardware. They try to do computations on a shoestring. And a good example is the Event Horizon Telescope, which sent hard disks around from one place to another to different pieces of the computation wherever they could get free computer time. And so the general property is that the computations are done where it is the cheapest or possibly free. And so in this new model, computations are really done very opportunistically. And by the way, it turns out that even now these days, some of the large MREFC projects are starting to adopt this model. For example, LSST was originally supposed to build their own computer center at Urbana. And now it's done actually on getting free computers and free resources at SLAC, and also sending some of the data to Lyon and to Edinburgh. So in this world, science needs really a robust cyber infrastructure with three pillars. One is computing capabilities, the other is fast networking, and the third one is a data-intensive infrastructure, which is still kind of missing. And once we actually have these mid-scale projects, which actually collect a lot of data, but they want to send wherever they can get free computer time. Data movement is becoming incredibly important. And today there is still a serious impedance mismatch. So in the storage layer, this transfers on the continental scale are still much slower than the network bandwidths. And many of the edge devices are on solid state disks, are capable only sending a few terabytes at a time. So on a petabyte scale, we still have a major problem. And so we had an idea a couple of years ago, so the Open Storage Network, and we basically created a standard appliance built on open software stack, but industrial microservices like S3, and so very simple API. And basically the idea is to have an inexpensive appliance that you can just plug into the 100 gig internet to backbone in the demilitarized zone, and then essentially it just works. And it can transfer data at wire speed. And we have today 8 nodes deployed. There's extensive testing, and the system is actually functional and in science use. So one can argue that, okay, but this is only temporary. In 10 years, everything will be in the cloud. So I respectfully disagree, because especially with this mid-scale, we build these high throughput instruments, which are typically located at the university. And so, for example, a transmission electron microscope, which is sending the data at a terabyte per minute bursts to an FPG array, which then does all sorts of data transformation and then wants basically to capture the data so that it can later on send to somewhere in the cloud or the nearest HPC center. And in order to capture the data, no matter what, these mid-scale projects will have to buy enough high-speed storage that they can capture these bursts and buffer them for long enough that they can actually gradually send maybe at 100 gig speed somewhere else. And so this can be beautifully solved with kind of appliances like the OSN pods, but one still needs to do a data transformation between the FPG array and, for example, the S3 interfaces of the storage pods. And so, but we didn't want to build it with OSN. We wanted to keep it really simple, but it's clear that for a wider science use, there's a need for a translation layer. And this is Valerio's project, the NSDF, the National Science Data Fabric, is really all about. How can we actually extend this philosophy to a customizable software layer? But this will never be actually obsolete. This will be needed even when we move things to the cloud, because we will always have to have kind of a low latency, very high speed and high capacity storage near these custom instruments that we are building in science. And I think as time goes on, we will be building more and more of those.
Alex, 1 more minute, please.
Yeah, so the data analysis is also evolving. And when we look at the evolution of the music industry, that's a good example. So we used to buy LPs and CDs and took them home and played it on our own devices. And this fundamentally changed with iTunes, where I could just download one song, but I still had to download it and play it on my own device. And today we have Spotify and Pandora, when everything happens up in the cloud and basically the data is just streamed to me and the AI is making the decisions on what songs do I hear next. So what is the data equivalent? Basically the LP equivalent is sending the tapes and disk from the site of the experiment to home, and then I analyze it on my own home computer. The equivalent of iTunes is having a SQL database where we can just get the data, exactly the piece of data that we need for this particular analysis, kind of one song at a time. And what is slowly starting to emerge, that running everything in the cloud like Google Colab, where the data sets are in the cloud and the analysis is happening in the cloud with a lot of AI involved, and essentially we actually stream down the results. And we are today kind of somewhere in the middle. So people are starting to get familiar with the iTunes model and gently probing kind of the streaming and the streaming AI. So we have over the years, over the last 20 years, built a bunch of key data projects at JHU, starting with the Sloan Digital Sky Survey. But in 2006, we started the J-issue turbulence database. We provided virtual sensors to large simulations of turbulence. And by now, these virtual sensors delivered 181 trillion data points to the world. And then we built recently AstroPath, which provided a 1,000-fold increase in data for cancer, imaging data for cancer immunotherapy. And today we had to process 16 trillion pixels, twice as much as the whole Sloan Digital Sky survey. And we are now just getting into Poseidon, which is building with MIT and Columbia the world's largest ocean circulation model with 2.5 petabytes of data. And so basically we are able to reproduce the SDSS experience based on all the lessons learned that we have done. But what we see are lots of commonalities, that the data is too large to store in multiple versions or multiple places other than the redundant security backups. We need to support a rapid failover to those locations, but we see multiple access patterns simultaneously. So people want on-the-fly immediate visualization based from the raw data because we can't pre-process the images. People want interactive Jupyter access to write Python notebooks, and then they want to be able also to do large scale-out computations where they can scale out, for example, to the Google Cloud, like Ryan Abernathy. And this means that there are many, many data transformations and transfer present, and some of them need low latency, like the Quick Look Wiz and Jupyter. But on the other hand, when we scale out to the cloud or we ingest the data, we need actually high sequential streaming throughput on petabyte scales. So how can we future-proof our computational model that can do all these things and also doesn't get obsolete in 5 years? So first of all, we have to come up with an architecture that can adapt over the years. For now, we need to keep the main long-term data out of the cloud because it's too expensive, as it was kind of discussed so eloquently earlier today. We need to move enough data, but just in time. And so, for example, AI training needs a lot of cycles, but for example, no long-term storage may need. So we could actually stream the data into the cloud, do the training there, the AI training there, and then just throw it away. And eventually we will also need to think about that some data sets are sitting in the Google Cloud, others will sit on Amazon or Azure. And how do we cross-correlate these data sets with each other? We will need to move petabyte data sets fast. And there will be always many different access modes, and we cannot store the data in many ways. So it must be easy to perform on-the-fly conversions. And lastly, we should not lose the focus on preserving the valuable data sets, because each of these big $1 billion experiments or even the $50 million experiments are basically, all the budget goes into generating a unique high-value scientific data sets which will exist for decades. Thank you very much.
Thanks, Alex.